All right. Okay, good morning, everyone. Welcome again. My name is Britton Smith, and I'm going to give sort of your second introduction following Matt's into how you should really be thinking about how YT works and how you should thinking about doing analysis in sort of the YT model. And that's what I'm going to talk about here. And we're gonna go through some very basic scripts. You can feel free to follow along, and you don't even have to type out a script in an editor and then run it. Everything you can do that I will show you here, you can just open a Python interpreter with Python, and then you can type one at a time if you want to. So that'll all work just like that. Okay, so the title of the talk is Objects in YT. Hopefully you'll understand at the end of this talk why objects are important. So what is an object in YT? Well, the short answer is everything in YT is an object. Okay. So what is it that makes an object an object? An object is something that has all sorts of variables associated with it. It has attributes that are variables that give you information about that object that can be changed, but they can be descriptive, and they have methods that are functions that do things to that object or with that object. And this is more or less what I will use for the definition of an object. Okay, this is thinking like object-oriented programming, for example. So to take a step back, everything is also an object in Python. So for example, if I have a simple script like this, and you can do this right in an interpreter, you can set x equal to 1. And then with any object, anything at all, you can type dir, and then you can type the variable in parentheses, and you will get a printout. Unfortunately, this is only part of it, but you should be able to see when you do this yourself that you can see everything that is associated with this. So this is a really important lesson to learn, not only for Python, but for YT, which is that whenever you encounter something you don't know what it does or what it can do, just go ahead and type dir on that thing, and it will give you basically everything that's associated with it. Some of those things will be useful, and some of them will not, but at least it will just show you basically an unedited menu of your options. In general, you can ignore the ones that have underscores in front. In general, sometimes you may want to use them, but usually you don't. So we've already seen two objects in YT in Matt's talk, and that was the parameter file and the hierarchy. There are many more to come, but those are two that you've already seen. You actually have seen others too. So for a little bit of a redefinition, hopefully Matt's definitions and my definitions will work together to help you sort of gain some insight into how these things work. So the parameter file object is really where all your analysis begins. Okay, this is the thing that is associated with your data set, and it contains attributes that are descriptive information about this set. It is often referred to as the PF. So if I just say PF during this talk, I'm talking about a parameter file object, assuming that you've sort of instantiated one. Okay, so here is sort of an idea of what you can get when you instantiate a PF. You can get information on the domain size, the dimension, is it a 3-dimensional problem, 2-dimensional problem, some cosmological parameters if this is a cosmological simulation that you're looking at. You can get file names and paths, so it'll give you the full path to this data set, things like that, for saving keywords for writing out data, things like that. We have a dictionary of all the simulation parameters, so you can look at every parameter that was used to run this simulation, assuming that these were stored with the data set. In Enzo, at least, they are. And we also get some very handy dictionaries of unit conversions, and also associated with the parameter file is this thing I already referred to called a hierarchy. Okay, so here's a pretty simple script. You don't have to do everything that's in here, but so every script begins with this import from yt.mods import star, and that pulls in basically everything into the namespace that you need to run YT and do analysis. Okay, and then the second line is basically where all analysis begins. Okay, so I do PF equals load, and I'm just loading in one of the data sets from the tiny cosmology run, you can load in any data set you want. Okay. In general, YT is smart enough to figure out the type of data set just from the call to load. Okay. And so then, for example, just as I said before, I can print dir of PF. Down here below the line is some of the information you'll get out. So when you instantiate a PF with load, you will immediately be presented with a number of descriptive pieces of information. So the current time, the domain dimensions, the left edge, the right edge. Is it a cosmological simulation? And if so, here are some cosmological parameters that you may find useful. And then, as you can see in my script here, I just print out a number of things. If you do this dir PF, you can see all these things that are associated with it, and you can just sort of, print them out and see what happens. So, for example, here I print pf.dimensionality. It'll give me dimension of 3. Omega lambda. Here's the full path. So this is the full path to that data. Here's the base name. These are helpful if you want to set keywords for saving data later. Here's the hydro method that was used. Here is some conversions. So we notice here that we have PF. Everything is PF dot something, right? All the associations. So we have PF dot units, and this is a dictionary. And so with dictionaries, we refer to things in hard brackets. And so the conversion to centimeters is here. Here's a conversion to megaparsecs. We have time units as well in pf.time units. With a dictionary in Python, if you want to see all the entries in the dictionary, you just print that dictionary dot keys. So if the dictionary is units or pf.units, you can print pf.units.keys, and you can see everything that is in that. And so this is very handy for doing on-the-fly unit conversions. And you can do the same thing with the time units, et cetera, and you can see all this stuff. So all this is associated with the data set. In some simulations, some of these units actually change as a function of time. So it's really handy to have all this stuff associated with that particular data set. Okay? All right. So the last thing that I said was associated with the parameter file object is this thing called the hierarchy object, which Matt defined earlier, but I'll sort of redefine again. Okay, so I like to think of this as sort of the gateway to accessing all of the actual data, the actual simulation data, the densities, the temperatures, what have you, of all the grid cells, of everything in that data set. This contains the information on what data is in what grid patch, where that grid patch is sitting on disk, and it also provides a lot of useful functions or methods for getting some quick information from this hierarchy. Okay, and it also provides access to all of what we'll talk about later, these data containers. Okay, so you don't have to worry about creating the hierarchy object when you create your parameter file with pf equals load. The hierarchy object, which you can access at either pf.h, pf.hierarchy, will just be instantiated for you. As Matt said, it is technically not instantiated right away because sometimes that can involve a lot of computational time and take a while. But the first time you refer to it, it will instantiate itself, so you never have to worry about making your own. Okay, it's just there. Okay, so here, for example, are some very useful methods associated with the hierarchy object. So all these should be pf.h dot these things. So they're pretty descriptive. Most of them start with find. We have pf.h.find max. You can put a field in there, and it will tell you the maximum of that field and where it is. A similar one will tell you actually the grid and the cell that it lives in. Here's a min one. Finding particles. You can find a point, find all the grids associated with an actual XYZ coordinate, et cetera, et cetera. Another nice thing about Python, which we utilize fully in YT, is that you can associate documentation with the code you write and actually access it as you run the code. So for example, you can always type help and then some function, and then you can see all the documentation that was written that was associated with that. And so that's really nice. Whenever you encounter a function, you don't know the function call, you don't know the syntax, you don't know what arguments it takes, you can type help on that function, and for a large majority of the code in YT, we've fully documented it, and it should tell you exactly how to use it, maybe even give some examples if we were diligent. All right. And if you need to instantiate an object in YT, what you want to look for when you type help is you want to look for the function called underscore underscore init underscore underscore. Okay, and that is the function that is called for any object to instantiate it, but that will tell you the arguments to give, et cetera, with that. Okay, so all right, back to a sample script that we're just going to continue to add to. We load in our data set. Again, I'll just type dir on pf.h, and we can see all the things that are associated with it. You can do this yourself because my screen only prints out the first few, which aren't super useful. But you can see all that's in there, okay? And then here's an example of running the pf.h.findMax on the density. Here's a further example where we use the cell location, and I have my values here, and we can see the printouts down here. So we show the max density, the max temperature. Here's, for example, what you get if you use this find max cell location. You can see the grid and its actual coordinates. So if you want to know exactly where that is, you can find it this way, which is really one of many ways to do that. Okay. So, all right, finally, we're ready to actually get at the simulation data. Okay, this has all been great, but analysis is about getting your hands on the data and manipulating it, playing with it, seeing what's in there. Okay, so okay, I lied. We need a quick diversion first, but then I promise we'll get right back. Okay, so I'm now going to introduce you to another object called the plot collection, which Matt did discuss briefly. But in a nutshell, the plot collection is a quick and easy way to make some of YT's plots. It doesn't make all, and it's a little bit limited in what it can do, but this is a really nice way to get at a lot of YT's functionality and make some plots very quickly if you want to see what's going on, if you want to do quick data inspection. Okay, and so the instantiation of this is pretty simple. Every plot collection is associated, it needs to know the PF it's associated with, and it needs a center. And the center is just when I make images that are slices or projections or things like that, where's my default centering in the domain. And you can see here, I do a really simple one-line code to know the domain center in this data set. It's just half times the left edge plus the right edge. All these things, again, associated with the parameter file, right? Mm-hmm. Yeah. That's a great idea. Yeah, if you have access, if you have YT up and running, please feel free to do this, with data. Okay, if you're using the Enzo data, for example, you see these directories, these DD directories. To instantiate, you need that and then the following ASCII parameter file that's associated with that. If you're using a Flash data set, for example, you just do load that one file name, and that will get it in there. Okay, so I'll calculate the domain center on the fly, and then in here I instantiate my plot collection. I associate it with that parameter file object, and I give it this default center. Okay, and then, so I won't go into all the things that you can do with the plot collection. This is really more going to be an illustrative device. But for example, we'll do a quick projection of density through the entire box. So we'll do pc.add projection, the density field, and the 0 indicates that we're doing the x-axis. 1 for y and 2 for z, for example. Okay, so you do that, and some magic should start to happen. And then finally you can save it. And so I've chosen to save it with the keyword that is the data set. So I use this pf.basename, and you should see that it's saved your ping file with something there, and you can download it and have a look at it. And so if you're using the data set I'm using, it should look something like this. Okay, so this is a this is a density projection, so what we actually get out is column density units of grams per centimeter squared. Okay, so this is what you should get for that, quick and easy. Remember, if you want to know other things that you can do with the plot collection, just type dir on the plot collection. Okay, all right. So yes, there's a ton more you can do with it. We'll get to that later. I really just want to show you how to use that so we can show other things. So now let's talk about the actual data containers. Let's talk about how you actually get to the data that you want to do the analysis you want to do. Okay? So the nice thing about these data containers that you still don't know quite what they are, but I'm going to tell you, they give you access to the data you want and only the data you want. So, you know, at least in Enzo, the file format is fairly complicated. Data exists in multiple files, and you have to know where to find it. And it can be a bit of a pain. You know, I'm not familiar with every simulations format, but, you know, the whole goal of YT is to not have to worry about being familiar with the format of any file. And we'll illustrate that in a moment. But the idea here is data containers, they're defined by their geometric properties and not by file formats and things like that. Okay, so all of these data containers, they hang off of the hierarchy. So what I mean by that is simply if I have my hierarchy at pf.h, a sphere is pf.h.sphere, you know, and everything like that. A disk is pf.h.disk. Okay, so here are some basic data containers that you have access to if you have your pf. Okay, so you can get the whole box right away if you do pf.h.alldata. You have a sphere. We have various rectangle regions. Unfortunately, that got screwed up a little bit in formatting, but we have a regular region. We have regions that recognize periodicity of the domain. We have rectangular regions that are off of the principal axes. We have disks, slices. We have off-axis slices, these cutting objects, projections, and even each individual grid itself is a data container. There will be more discussion of more advanced data containers to come later in the advanced objects talk. So let's look at one of these objects. Okay. So again, we load it in the data. We choose the center. I have my plot collection, and I would like to center the sphere on the maximum density. So you can do this in a couple ways, but I've chosen to do it sort of the more brute force way. I use my find max method from the hierarchy that gives me the center stored here in my location. Max row gives me the actual maximum density. Okay, and then I say it's going to be my sphere. You can call it whatever you want. It's pf.h.sphere. I give it the center, and over here I'm specifying the radius of the sphere. Okay, the actual radius is specified in code length units, but you can see how I use this units dictionary to forget about the code length units and say I want that sphere to be 10 megaparsecs in radius, and I can use this dictionary to do that. So 10 divided by the pf.units megaparsecs. Okay, so now just like on the previous example, I will add a projection with the density in the x direction, but as well now I will use this keyword argument data source equals my sphere, and what this is saying is I want to project just my sphere. Okay, and I'm also projecting another field, this field called ones, which is actually just sort of the cell width. Okay, and then I'll save these things. pc.save once will save everything in the plot collection, which is both of these projections. Okay, and so this is what I get. All right, so you remember the whole volume. We had a nice cosmic web there. Well, here's my sphere centered on the max, and yes, it does recognize periodicity. So here's the bottom of it, the top of it wrapped around on the bottom of the domain. So this is just to illustrate to you that yes, the sphere really is a sphere. Okay, here is the cell width through that, so you can see that it's round, right? So there's sort of like a limb darkening type of thing. So, okay, all right. Here's the nice thing. So we haven't actually accessed any data, but it's really easy yet. Okay, so accessing any data in an object like a sphere is as simple as saying my object, my sphere, whatever it is, and then in hard brackets, like a dictionary, the field that you want. So that could be density in quotes there. All right, and you can try that and see what pops out. Okay, and we're going to do that here as well. This time I'll instantiate a different object. I'll instantiate a rectangular prism, which is a region. I'll use a periodic region because, as we could see, my sphere was on the edge. The difference, in case you're wondering, between a periodic region and a regular region is that regular region has some simplifying assumptions that makes it a little bit faster. So if you know that your object's going to be in the middle of the domain, you don't care about periodicity, you can forget about using a periodic region. It'll be just a hair faster. Okay, so again, I find the max, and this time I just have to specify the center, and then the left corner, and then the right corner. This, again, is an array, and so if I add this, this is all just the vector math it adds to each element. And so I'm going to make it this time 10 megaparsecs from the center and 10 megaparsecs from the center on each side. Okay, and now once I have my region, say I want all the temperature values within that region. Well, it's as simple as saying my region and then temperature, and then you can see what's printed out. It's a nice long string of all your values. It's an array. We can find the position of each one of those grid cells by doing print my region and then say x. It's the x position, y, etc. But any field, all you need to do is do that, and boom, there's your data. Okay, and it doesn't matter what files they live in. The hierarchy object is really doing all of that work behind the scenes to ensure that you don't have to care about that. What you need to care about is the physical objects you want to analyze. Okay, so when you do what I just said, so my region, temperature, density, whatever, these data containers will return to you field or particle data as a NumPy array. So, you know, an array that is manipulatable with, you know, standard array math. You know, you can add them together. You don't have to loop over each cell, for example. So we can do some nice things because they are returned as NumPy arrays. So again, this is just a tiny edit to what we've been doing. Again, this time I'm going to use a disk. I'm just use a different one every time. So I'll have a radius, I'll have a height. I've specified these in code units. You'll see why in a second. So I give it the center, I give it the vector, which direction that disk is oriented, the radius, and the height of that disk. And now, for example, let's say I want to see the density of all the points in the disk that have temperatures greater than, say, 1,000,000 degrees. So the density of all hot gas in this disk. Well, it's simple as saying, first, this goes from right to left. So we have here my disk temperature, so that gives us all the temperature values, and greater than 10 to the 6. This will return to us a Boolean array, true falses, of all the array elements in this data object that satisfy this criterion. And then we can simply use that as basically a filter. So we'll just add these hard brackets around here, and we're doing the density. And this, again, will print the densities of all those cells that satisfy this criterion. Okay? It's that simple. All right? Which is really nice. Okay. So the really great part about YT and all of this is that everything that I've done is completely independent of simulation code. So here is the exact same script. The only thing that is different is that I'm loading in a Flash data set. And everything works identically. Okay? Of course, the data set has different data units, so you're going to get something different out. But everything works just the same way. All right? And any other code that's supported, yeah. Yes, so that's a good question. We have made it such that those file names also can use the standard density temperature. Yeah, and I believe you can do both. Someone can correct me if I'm wrong on that. Yeah, there are aliases. Precisely. Yeah, I also like to point out, once I get my act together, all these scripts, all these example scripts will be made available as well, in case you didn't have time to type everything that I'm showing up on the screen. Okay. So just to further this, even the grid patches themselves, the things that I told you not to care about if you really want to, even those are data containers. Okay? And so I can access them with pf.h.grids will be the array of all grids. If I want to look at the first one, if I want to look at the density values, it's as simple as that. Okay, and if you remember this example from earlier where I use pf.h.find max cell location, and I have all of these return values, my grid is returned. My grid is that object, is that grid object from the hierarchy. And so I can simply then do my grid temperature with that coordinate. And so if you do this statement and print my value, which was returned as the max, they should be exactly the same. And they are, at least in mine, even though you can't see it down there. Okay. So to wrap this up, let's put it all together and just sort of give you an idea of what the workflow should be when you're using YT. Okay, so you start with your import. That should actually be step 0, which I didn't have up here. You create your parameter file object with the load statement. You create your data containers, whatever they may be, a disk, a region, a sphere, whatever you're interested in. And then you access the data with those containers just as simply as my object and then that data field, and then you do whatever it is you do to bring home the money. So, and then, of course, if you want to make some simple plots, you can create a plot collection object, and that will give you a lot of sort of shortcut access to a lot of the things that YT can do, and plop out a plot. It'll be less customizable as other things you can do, but you can still do a lot with it. And a couple of other reminders as I sort of set you off on your grand journey. The plot collection is only one way to make plots. You can do a lot of others. And if you ever encounter something you don't know what it can do, you can type dir on that thing. You can also just type dir with nothing in it, and you can see what's in your namespace after you've done your import. But this is the really important one. Dir on some object, it'll tell you what you can do with it. You encounter a function or an object you don't know how to instantiate. So if you don't remember the arguments to sphere, you can type help pf.h.sphere. It'll tell you all about it. And that should be all you need to know. So yeah, go have fun.